The uh, the the proposal is, I think, a bunch of discussion that happened in a few contexts. And I think some people might remember there was a workplace post. There is a bunch of issues discussing this topic. And the idea would be to introduce a concept of accelerator. So what we mean by accelerator here is any device that we consider to be running asynchronously from the CPU and that would be mutually exclusive between each other. So the kind of things we have in mind would be CUDA, HIP, MPS, MTIA, and private use one, I think would be the main ones we have right now. Some from Intel, I never know which one is which with the Intel devices, but a couple of them should definitely be in that list as well. The goal is that we want to enforce only one of them is available at a time, and then that should allow us to have some generic APIs for us to implement feature that will work with any accelerator that follows this concept. The benefit is that a lot of these have common concepts like RNG, streams, events, availability, things like that, and we want to be able to write non-CUDA specific or more, and with ROCm, MTIA, and private use one being big pushes that people want to do in the code base today, I think there is definitely something that we need here to preserve some sanity. So that's the top level pitch. The implications here would be mostly around a couple things. We would have a more uniform device module on the Python side. So there are some APIs you can expect to get for every device so that you can write more generic code. We would have a similar thing on the C++ side where we would enforce a bit more what is available for each of these accelerator style devices. We would update pin memory concept to be associated with whatever is the accelerator available and not just CUDA as it is today. And we want to add a bunch of build some of the common infrastructure that we're missing today, in particular around stream and events. MTIA needs that pretty soon. And then more open-ended timelines. We definitely would like to look at a bunch of the features we have that are today very CUDA specific, or CUDA plus private use one specific for a lot of them, like the AutoGuide engine, activation checkpointing, FSDP, these kind of features, and rewrite them in such a way that they use the current accelerator. The goal being that hopefully that will smooth out significantly the MTIA integration and simplify the code on our end or simplify the logic on our end. So yeah, that's the 5-minute pitch.
Thanks, Albin.
Any questions?
Yeah, questions? Go for it, Brian.
I guess we have a bunch of APIs, and how much of the work do you think is figuring out what to do with all the existing APIs and rationalize them versus new API accelerator? And maybe one I'm thinking of in particular is we have backends can register their own modules. You can do torch.xpu, torch.whatever. Should we just have both in the long run, or is that not part of this discussion?
No, I think a lot of these backend modules, as you mentioned, for backends to register their modules is what I would say was a good first step that we did in that direction of being more uniform about having backend modules. I think the proposal here is to embrace that and say for the accelerator backend, we would actually enforce what is available in these modules a lot more strictly and actually start to leverage that. Because today we have them, but I don't think we leverage them that much, mostly because a lot of these things are just not available for MPS or for CUDA.
Okay, that makes sense. Thanks.
Any other questions?
Wait, so is accelerator going to be its own backend? Or what is the difference between backend and accelerator in this new world?
Accelerator is a completely independent concept from backend. So accelerator is you basically will have one API that gets me the current accelerator. It's a global concept, but that's it. So if you want to, send your tensor to whatever is the available accelerator, you just get the accelerator and set it to there.
Sherlock?
I'm wondering if this effort is focusing on the eager behavior, meaning that the concept of accelerator here is more like a device, and it also get its own dispatcher key, but in contrast with a backend register as a dynamo backend, which is a compiler thing, where they probably don't they take a graph and then they don't need a dispatcher key. So how do you draw the boundary here?
There will be no dispatch key for the accelerator. As I was telling Jane, this is a purely one step higher concept. So get accelerator will give you CUDA if you are on a CUDA machine. And then, but the goal is to have, this is not an effort to change the way the eager backend is implemented. It's an effort to simplify how framework features are implemented. And that's why I mentioned activation checkpointing, a lot of the distributed constructs, autograd engine, these kind of things where we want just a more common API to work with all of these devices.
Michael So?
You might have mentioned this and I missed it, but have we gotten feedback from the MTIA folks on the design for the accelerator API?
No, because the person I have in contact there is on PTO. But yeah, I am planning on discussing that with them, yes.
Yeah, I mean, right now they're very inference focused, but the next generation chip is training. And so, I mean, they should probably at least be aware so they can kind of build their stuff around it.
Jansen?
Yeah. What I would say, Michael, as well, is that a lot of this effort on my end is driven by the fact that they asked for a bunch of these related concepts. And instead of adding more ad hoc if statement, basically, I think it's a good time for us to build a little bit more structure.
Yeah, exactly. I think that's great.
So yeah, MTIA is definitely the number one customer here.
So another person to talk to is you should talk to the Intel folks. They've been submitting some PRs to do stuff like common stream APIs across multiple devices, and that would flow into this. I'm wondering if we're enforcing the invariance that there's only one accelerator at a time, does that mean we can have one dispatch key for every single accelerator?
I don't think so. I think there is still significant possible changes. Okay, the real answer here is from some discussion with Ed, I'm not sure we can at compile time enforce that invariant. And for motor repo reasons, I could see a world where some people will have both CUDA and MTIA enabled, and they don't want to go through the pain of figuring out how to disable one or the other. And so I think it's not a constraint that I'm ready to see, very hardly enforced going forward, even though it's definitely not in a stage where we will allow changing the accelerator. But it might become a runtime flag, or like a runtime environment variable that you have to set, and so we cannot really, remove dispatch keys, or at least that's not the goal right now.
Tris?
Is it possible to have a heterogeneous mixture of accelerator? I don't even know if that's possible today, but 20 years from now, you have MTIAs and CUDAs and all these crazy accelerators.
Yeah, I was actually going to ask the same question because like the Grace Hopper hardware we're getting, right? We want to co-optimize between CPU and GPU.
Yeah.
So it's not 20 years.
20 minutes from now.
So CPU plus accelerator is definitely fine, and that would not be a problem. I think it's it seems not future proof. It's not future proof, but for it expected, right? What I will say is the kind of feature we're trying to fix is like we're trying to improve the behavior of is activation checkpointing, FSDP, these kind of features. If you want to collocate stuff and do a distributed aware system where you know about an MTIA device is here and the GPU device is here and you need to do some fancy stuff, you will not be able to use off-the-shelf generic features we have, or as we're gonna have written them. Like there's no way you can just use them. So you will have to do custom logic, or we'll have to add these completely new concepts on top of what we have today anyway. So I don't think it should prevent us from doing that today.
All right, thanks for the lively discussion. All right, let's move on to the next portion. Brian, do you want to pose the problem, or do you want me to try?
I can try.
Okay.
So I don't have like a design doc. It's not super fleshed out or anything, but I also think we've talked about this before, but it's like worth talking about again. So I'll lay out the problem, which is torch.compile plus like communication ops that are at the end of your compiled region. And so let's say you're like compiling a model and the model ends with an all gather or something, or reduce scatter. And what is the current state? So the current state is that we compile a bunch of graphs in partial graph worlds, and one of your graphs ends in a reduced scatter or something. And we will synchronously wait for your reduced scatter to finish before exiting the compiled region and moving on to the next piece of like Python code in the user model. And so A, this is like fine for correctness. B, this is like maybe not good for perf. Open question on like if this is bad for perf always, or if this is like maybe you have a bunch of graph breaks, so you have 10 graphs, and now there's a bunch more comms ops at the borders, and now we're syncing a bunch of times, and you can like solve your perf issues by reducing graph breaks. But like maybe that's something we should fix. And like, what does it mean to fix it? It means it would be nice if you could run some code that you compiled where the compiled region that you're executing at runtime ends in a comms op, like a reduced scatter, and then that reduced scatter is like running in the background asynchronously, and in the meantime, Dynamo moves on to the next graph and is like starting to compile or run the next region. So any questions on problem statement? Sherlock, do you have a question, or is that old hands?
Yeah, that's all hand.
Oh.
No, yes.
Yeah, so I mean, one question is like, when should we fix this? And maybe the answer is just once we see in some real model that this is like a crucial bottleneck or something. But then separately, like, what's the way to fix this? So I think concretely, how is this like asynchronous collective stuff implemented today? And there's a bunch of distributed people on the call who did all the work. Of today, there's this async collective tensor subclass. And it basically it is a subclass that like represents the fact that there's some asynchronous work that needs to be completed. And the way it works is you call some comms op, like reduce scatter, and instead of returning a tensor, it returns this async collective tensor subclass. And it will return that subclass immediately. And then your comms op is like running in the background. And then the next time you use that tensor by passing it into another operator, this async collective tensor subclass will realize it's being used in an operator and then perform a wait before actually using that that tensor in the next operator. And there's like a few things that, there's like a few things that I imagine will break today. And one that I can think of off the top of my head is like that logic involves a bunch of global state. There's this like global mapping between like process groups and like the data pointer of the tensor that the process group is tied to, so it kind of knows what to wait on. And like all the like this is all stuff that we're like tracing at compile time, and so that like global map will just kind of be the wrong thing if we're like burning stuff into that map at compile time where we have like fake tensors without real data pointers and stuff. So that is like one set of things that probably is going to break. And then the other that I was talking to Ed about earlier today is how like streams fit into all of this, where supposedly like you have a bunch of tensors returned from your graph and they may or may not be on different streams. And how is that like represented both in general in compile, which is something that Jason has like thought about for a while, and also like how does that tie into the async collective tensor subclass? So yeah, that's about as far as I'm in like just talking about it. But any questions or Ed, anything you want to add?
No, that's a good start. Questions, comments? Okay, Wanchao, go.
Yeah, I was mainly like if we put the stream correlation away and we just think about the current collectives, I'm wondering is that if this first of all, I feel we should find a motivating use case for us to do this. Second is that I think if there's a motivating use case, or even if there's not a motivating use case, a single thing we can do is that when we trace this subgraph and the last node, maybe the output node is a collective that contains a weight immediately, I think we can just return a rapid as a async tensor subclass and then put it back to the like return it as a subclass and then then basically allow that subclass to run eager mode. I'm not sure if that actually could just work for all the cases, but at least that's the thing that I think makes sense to me. Yeah.
Okay, I'm going to pipe up for a moment. So actually, I guess this is interesting because I actually wanted to ask the reverse question, which is, does it even make sense to solve this problem without considering streams? Because like, you know, one way Brian could tackle this problem is he's like, well, async collective tensor is a tensor subclass, and we've got some machinery that knows how to deal with tensor subclasses in abstract. So I suppose I could try to solve this problem where, you know, if I return an async collective tensor, I somehow try to figure out how to produce an async collective tensor in the end, because that's what we're supposed to do when there are subclasses involved. So Wanchao, I heard from you, you said, actually, you know, what if we just like start sprinkling in async collective tensors whenever there's a collective at the end? That is indeed a legitimate policy decision, but I'm trying to get the temperature on like what people think. Because for me, it's hard to think about, I really want to solve this simultaneously with streams because they do feel very related.
I kind of want to counter that. I haven't been convinced that we want to solve streams badly enough to actually solve them because they're hard. So it's a good idea to solve, but when we use these tensors for things like detensor ops for tensor parallelism, I don't think we usually have to activate a particular stream for that. And in the FSDB case, I guess the streams are handled differently for compile anyway. Like, is there really a strong reason to need to model streams differently than we are today?
Jansel, what's your current take on this situation?
Yeah, so I think there's like really like two classes of streams. So one class of streams is compute streams, where you're like parallelizing, you know, two map models or something like that. And the other class is communication streams. And I think we should basically entirely ignore compute streams because I think they're gonna, like, having stuff on separate streams is gonna prevent fusions, and I think in general, like, Inductor should be able to do a better job generating multi-stream output code. So I think we should just discard compute streams entirely. For communication streams, I think it would be. I think there's much more of a need to respect streams in the original program, and I think that's also a lot easier case. So I think we need to not necessarily like model streams in entirety, but I think like basically having respecting user streams for communication collectives, I think is like relatively tractable to build and would solve this problem.
Can you say why? Or is it for FSDP or is it for other tensor parallel use cases?
I mean, I think because like usually the pattern in a lot of these models is you have like a communication stream and you have a compute stream because you're trying to overlap communication and compute. And I think it's reasonable to say like our cogen should put if like the user put a communication on the communication stream and didn't wait on the communication stream, I think it's reasonable to say that like our generating code should do the same thing.
But in eager PyTorch, do we actually have users using the communication stream in their code? Or I guess maybe for ads models they would. But C10 internally has its own communication streams that it uses underneath. So it already doesn't respect streams as users. Like we just kind of sync back to whatever stream the user was using and use our own streams, which may be something we would want to change. We wanted to really respect streams people gave us.
Wancho?
Yeah, I just want to get some, like I think as far as I know, all the parallelisms that we've seen so far seems to me only FSDP need to actually have a user stream to control, like specifically put your communication on this user stream. And all the other parallelisms seems like they can easily do it with the process group built-in stream. So I think the question here is that should we sort of model the stream in the compile stack that is consistently with the process group behavior so that these two can actually be modeled into a same communication behavior there. So currently I think we're like just like sort of I feel we're just like working around the problem by like putting the communication up in the graph and then rely on sit&d to do this. Yeah, so I think this is something I also want to hear more about from people.
Okay, so I mean, part of the reason why Vaz, bless his heart, was not rattling around streams was because he was working on FSDP. So I don't know what the plan is for FSDP, but actually, Will, go ahead.
Yeah, sorry, yeah. I was looking into FSDP for the past few days. It seems to me that we can just disable stream there and let inductor reorder the collectives to achieve the same behavior. But this is only my preliminary understanding.
Okay.
So we don't have to model stream for FSDP.
Okay, so this is fine. So then, Brian, okay, so okay, go ahead, NYC.
I'm not. I don't know if Andrew is here. But if he's not, I would like to comment on that one. That stream usage is pretty critical there, and in particular to achieve the memory usage that you want and the overlapping that you want, you need very careful stream usage. And I'm not saying inductor cannot do some stream usage by itself, but we need a user input about how we want to trade off overlap with memory. And I don't think inductor can just guess that because different users want different things.
Okay. Albin, your message is noted, but for the purposes of this particular conversation, I think it probably, so in particular, Brian, the model you're looking at, which prompted this question, is not using communication streams in a non-trivial way. Is that right?
That's right. I honestly wasn't even looking at a particular, well, I think that's right. Yeah.
So I think it's probably safe. I've been convinced that it's safe to consider the simplified case where there is only the C10D managed internal collective stream. So for the interest of moving the discussion forward, I want to give a straw proposal, and then y'all should tell me why it doesn't work. So the straw proposal is whenever we return a async collective tensor. Whenever I return an async collective tensor, I still return an async collective tensor, and I have it wait on the PG stream ? And when I get an async collective tensor as input, I do a wait on it inside of at the beginning of my inductor compiled graph. There, that's my horrible, not very good proposal. All right, please poke lots of holes in it. So my horrible, no good proposal is that whenever I get a async collective tensor as an input, I call wait on it before I do anything else in my inductor region. And when I return one of them, I just, the semantics of it is to wait on the C10D internal communication stream.
I think like in the common case, that'll work for everything except for the case where you want to overlap communication across iterations. Like if you have if you're trying to get like the last collective of iteration I to like overlap with the beginning of the next iteration. And the question is that an important use case? Is that something that like, is that something we can solve in sort of a simpler way? But then I think I'd envision that being a challenge.
Why do you not get that for free with the version Ed gave? So I guess what I'd imagine is like, there's a weight in the graph somewhere on the input, but then inductor is free to move the weight to the latest place it's needed. And so the like async thing from the last graph is free to run at this while the beginning of the second graph is running.
I guess Ed was saying we just wait at the beginning, but I guess like if we intelligently scheduled the wait right before it was needed, then that would achieve it. Or is that what you're proposing, Ed? Or
yes. Okay. We have added the intelligent proposal to the proposal, plus intelligently moving weights. I actually have some questions about this, but it sounds plausible.
For what it's worth, I feel like this, in theory, should just happen automatically. Like today, we get an async collective tensor as a graph input. We desugar that into a new graph where the input is a plain tensor. And then as part of tracing, like a weight shows up in the graph when we just like trace the function where the async collective tensor was the input. And now there's a weight in the graph, and if inductor wants to move the weight, it can, or it doesn't.
Okay.
But I feel like probably.
So ask my question: does weight actually work in inductor graphs / like AOT autograd? Like, can I actually put one of these inside a Dynamo produced graph, and then it'll like properly get preserved by AOT autograd, and then like actually do a weight in inductor?
If I remember correctly, I think the weight only getting in line in AOT autograd. Dynamo would just have a sort of a collective of there.
I think you would never see a weight in the Dynamo graph. You would only see async collective tensors in the Dynamo graph, is my understanding.
Sorry, I guess what I just mean is that okay, so AOT autograd can produce graphs with weights, and then inductor can ingest graphs with weights, and this works. Okay.
I think that's right.
Okay, cool. So it sounds like inputs are okay. What about the output thing? Does the output thing work, Brian?
I don't know, because we don't do it. Because today, what happens when you're compiling, in theory, every time there's an async collective tensor, there's some logic that says like immediately issue a weight as part of tracing. And so you'll never see an async collective tensor output today.
I personally think that the biggest area we have to solve here is in mapping the tensors and the async collective tensors together in some reliable way. Because other than that, it should just work.
Will, can you tell us more about this problem?
Well, I'm not even sure if it is a problem. It might work already. I think that was the premise Brian brought up in the beginning as a problem statement. It's like that we might not have a way to map fake tensors we trace to real tensors or something, which I didn't quite get because we are tracing async collective tensors today. It works. But I think I'm missing something. In this case, we'd be creating a tensor in the inductor graph, and then we'd be creating a new async collective tensor. We should still be able to follow the same creation logic as we use outside of inductor, which would register the tensor in some map of tensors and work objects. And then we can call work.weight.
So just to be clear, well, this is only the output tensors, is that right?
I was talking about tensors we're outputting.
Yeah, output tensors. Okay, so then the not so horrible proposal I'm hearing is something like for output tensors, if the tensor is weighted on, but it's the result of the weight is not otherwise used, and the result is an async collective tensor question mark, then instead of immediately weighting, don't, and instead register that tensor to the global map in async collective tensor and then produce an async collective tensor.
Right. Yeah, exactly. We shouldn't have to wait. We shouldn't have to force a weight on graph break. We should be able to delay the weight until it's used, whether it's used in eager or whether it's used at the next inductor graph.
Okay, so Brian, I want you to ponder this. Like, does this actually sound implementable, or is there like a problem?
Yeah, I think I kind of agree with Will. Like, will anything bad actually happen? I guess maybe two concerns I have. One is it'll be hard to. So today, my understanding is like the reason we issue the weights immediately when we're tracing under like when we see async collective tensors under compile is so the weights like show up in this nice, easy to reason about way in the graph where like inductor always gets to see like comms up and then weight in these nice pairs, and then it can do its own reordering. And I think it'll be hard to do that, to like keep that current functionality, if we also want some way of being able to say like, if we see a comms op, don't actually wait immediately during tracing because this comms op might be the output of the graph or something. And maybe that's fixable when we just like do some extra logic to like fix, so inductor is aware of the fact that weights might like show up later or something.
So when we're tracing, we can just do the weight because it's a fake tensor weight and it shouldn't actually do anything. And so like basically what we'll do is we'll get a graph that has the weights in it, and then like what you can just do is you can just check like, okay, is the return value of this weight used in the graph, and if not, just like drop it from the graph, like just have a path, an fx path that deletes the unnecessary weights.
Yeah, I think that's true.
Yeah, it should be a pretty good invariant. Like either you use the weight in the graph or you ensure that you return an async tensor that'll make sure the weight gets used later. Only two cases.
I think there's at least one more thing we need to change, which is like the way we even detect that when we're tracing the graph, we need to detect like, are any of the inputs or outputs of the graph subclasses, and then do something special in that case. And part of the way we even detect that in the first place is by just like vanilla running the graph with fake tensors and then poking at the outputs and seeing if they're subclasses. And if we like during tracing, we immediately wait on every async collective tensor as we're tracing the graph, then we won't see that the outputs are async collective tensors. So I guess I think I agree with all that. Plus, just we'll need to do some other work somehow to figure out like the outputs of the graph are subclasses, so we need to do something different.
So if we're willing to convert tensors that were not necessarily actually async collective tensors in the original user program into async collective tensors, we could just it doesn't matter if they are async or not as far as AOT autoguard is concerned. What really matters is if, I guess, inductor or whatever FX pass is looking at it, whatever thing tells me, hey, these outputs, please wrap them up in async collective tensors because I didn't wait on them. I need you to wait on them for me.
I mean, can that wrapping just happen inside the inductor general graph? Do we actually even need to know? Because I guess in my ideal world, these async tensors and regular tensors should be pretty interchangeable. And so you potentially outside of the graph, you don't even need to know that something's an async tensor. You can just treat it like a tensor.
Yeah, I think that's fair. If inductor is the one handling async collective outputs, then yeah.
Yeah, because if it's an inductor pass that's deleting the weight, then that the deleting the weight should be creating the async tensor.
Wanchao?
Yeah, yeah, I want to step back a bit. I think yeah, mostly I was trying to think more about what Jason mentioned previously about the communication stream stuff related to FSDP. And I was thinking that if it's possible, the current lowering for communication is you capture it in Dynamo and AOD autograd with a collective op, and you just lower it into an inductor IR, and the inductor codegen will generate the PyTorch distributed collectives there. So I'm wondering if after the inductor, I'm wondering if inductor should model the stream as a first class concept, and then whenever you I think process group ops, they are just associated with a stream, and then when you're lowering in inductor, we should possibly try to model lower this into a stream set of IR instead of currently still relying on the CTB thing. I'm wondering if that's a good idea or not actually. That basically makes say user stream in FSDP, it will go into inductor, and inductor will actually have a stream ops with respecting the FSDP stream, and similarly for all the collective ops, you get a similar thing. You get the same you get a separate stream that is associated with CTD, and but the inductor can actually model them consistently. Does that make sense?
I think we could do that, but the thing that I haven't figured out about dealing with streams is whether we want users to be aware of the ones we use in inductor. Because if we made streams first class only inside inductor, and then we have inductor manage a communication stream, but then if the user didn't know about that, when we return back to userland, when we graph break and go to eager, I think we still have to synchronize that stream that inductor used for communication back onto some other stream. And either it has to be a user stream for communication, in which case, then we really should have a good contract about the user stream is the inductor stream, or it's not, in which case it's probably just the main stream. And then we're kind of forcing a sync.
NYC?
I have a separate comment, so I don't know if this thread is done. Okay, I guess yes. I think from what Will is saying as well, I definitely agree that it might be tricky for us to have inductor stream be completely independent from the main streams. I would be curious Ed or Jason, do I understand correctly that one of the key challenge we have with streams is that modeling them at the dynamo level and at the pre-AOT dispatch level is something too challenging, and we don't want to do that. But at the inductor level, it's definitely on the table to have full-fledged stream support. Is that accurate?
So at the dynamo level, modeling streams isn't that hard. You know, you can just wrap them and stick them in the graph as stream ops. Yeah, one of the challenges there is at the inductor level, there's, I mean, you could model them at the inductor level, but like modeling them at inductor level would involve some changes to the scheduler, because you basically want to you'd want to make the scheduler sort of aware of streams. Streams would like prevent fusions, because like you know, if you have two ops that are on two separate streams, you know, can you move the op between the streams in order to fuse it? And also there's work in inductor that happened last year, where inductor will actually generate multi-stream code. And that multi-stream code allows sort of kernel-kernel parallelism on the device. And in general, I think the trade-off between respecting user streams versus like having inductor generate its own streams, I think that we're probably better off with inductor generated streams, because most user code doesn't use streams at all. And so like this is like a relatively uncommon case. And if a user has like crafted like compute parallelism on streams, by fusing stuff together in inductor, we're probably going to like mess up the balance of ops. Like maybe like the user had like a bunch of pointwise ops that were running in parallel with the mapmul, and then inductor fuses all the pointwise ops into one op, and all of a sudden it's way cheaper, and like it doesn't make sense to put on a stream anymore. And so I think just like we're in a case where like for compute parallelism, we're just better off. I think we should be correct. So basically, you know, one easy way to be correct is like you look at all the streams in the user code, and you basically just introduce like a barrier at the beginning of the end where you just add weights from all the user streams. The user can't actually tell that inductor ran stuff on different streams. But I think we're like in order to just generate the fastest code we can, I think like the correct strategy is throw out all the user stream annotations and regenerate them from scratch.
Okay, so then the tension here is not as much about the technical implementation, but when do we actually want to preserve user streams or not? Because it feels like for, as you said, right, for compute, we don't want to, but for communications, we do want to.
Yeah, and for specifically for the case where like the user has like, yeah, I know there's some cases in distributed where like the model authors have basically like hand inserted a lot of collectives into the graph, and are like have like really like crafted like, oh, like here's this long running communication op that I want to like parallelize with this layer, and like there's use cases like that where you know, you have sort of like communication ops that span like much longer periods of time. And you know, I mean, you could make a similar argument. You could say like, oh, like maybe it makes sense just to have like, you know, inductor can parallelize these types of ops, and we should do that. The case where those cross graph boundaries is the one challenge there. Yeah, I mean, I could be convinced that this is true for communication as well, but I'm definitely convinced that for compute we should just ignore user streams.
Okay.
Well,
So
sorry, go ahead.
is what I hear then that if we say, let's say I have a way to tag this stream to be communication stream, then it's on the PT2 stack side, we would be happy to just preserve that throughout, and we're happy to do that.
I mean, we could do that. I guess there's like a few design things. Like, so one is, so one like design path, it would be, okay, we're gonna, every collective op, we're gonna tag it in its metadata with which stream it belongs on. And when we do code gen, we're just gonna respect the original stream of collective ops. And then we'll like regenerate all the syncs based on the output kernels. That would be one strategy. Another strategy would be to say, like, okay, we're gonna really embrace like async tensors for doing stream management, and we're gonna say like okay, users, don't sort of like handcraft all of the streams for collectives. Instead, just use these async collectives. The async collectives sort of under the hood have their own stream. And if we just assume that everything's an async collective, then there isn't really any stream data you need to preserve. But that's a more limited model because the sort of class of things that you could do with async collectives is less than sort of like full control over full fidelity streams. And so there's a question of, do we need that full fidelity streams for communication? And for that, I really just defer to people who are more expert on distributed than I.
Seems like the conservative thing to do would be to add a new way for users to say, like, you do everything, but for us to respect the existing sort of fine-grained stuff.
I have one more concern. I'm not sure if this is accurate or not, but I don't know if we can separate communication and compute streams, because, like, if you take the FSDP case, one of the things they put on a special stream is the copy kernels that are going to be the inputs to the communication. And so unless you also include the copy kernels in modeling like this side stream, you still need to have some way of preserving some CUDA event that came from the original compute user stream and syncing that to the communication stream. So I think things bleed between the two buckets.
So you think we should just like go with sort of the like async tensor approach, where basically say like, okay, we're going to ignore streams for collectives and just return async tensors from the graph and then take in async tensors as inputs?
Yeah, I think this strategy seems promising, and I kind of feel like the other strategy, if we want to do real streams, it's really hard to get it right. So I thought about it a few times and I couldn't come up with anything that I felt very good about.
Oh, sorry, Will, I'm confused from what you're saying. My understanding from you saying that we have a bunch of copies, we have a bunch of special kernels we need to run on these side streams as well, would mean that the async collective tensor is not enough. We actually need other stuff that just the async collectives that run on the side stream. We need a bunch of supporting kernels next to them.
Sounds convincing, but I think it's not correct. I think Vaz and I figured out that we could flatten FSDP by tracing it, and that it would still be correct.
Okay,
so if the like distributed folks are saying that async collectives are sufficient, then I think it is way simpler and way better to just completely ignore all streams and only use async collectives. I think that's basically like the key question there is that enough? And I think we should really verify that and test that. But if it is enough, it's a way better plan.
I'm personally skeptical. The reason for that is in FSDP, a lot of the realized memory usage we have is by orchestrating the allocation, copy, collective copy out in a separate stream with very specific weights. And I'm not sure if we're going to be able to do that with just the async collective.
Albin, you also believe this even if you have some, hypothetical inductor memory planner that's making good choices?
But the problem is that what is a good choice here? I think the crux of my problem with that is there is no good choice. It's like a Pareto optimal choice of how much you want to overlap, how much you're ready to spend memory. So there's no one true solution that the inductor optimizer can find.
So one thing we could do is we could say that we have a memory planner that takes a memory budget, where basically the memory planner is required to keep the program under some memory budget, and then you can basically use like max flow min cut, so like the same type of algorithm we're using for the partitioner to sort of find sort of the point in the program where memory peaks, and you can do sort of some reshuffling to try to keep under sort of that memory budget. It's like really like the main reason why people would be doing sort of this like handcrafting stuff would be to decrease peak memory usage. And there are trade-offs there, but like I feel like the trade-offs could be expressed as, here's your memory budget, stay under this memory budget, and if you can't stay under this memory budget, then throw an error.
Do you think that is a feasible plan in the partial graph world we live in?
It would have to be a memory budget per graph, most likely, and maybe we can auto-generate the memory budget by like looking at like the available memory, yeah, I mean, I think there is a trade-off space here, but I feel like it's a one-dimensional trade-off space, and a one-dimensional trade-off space you can like express by sort of maximize communication overlap while staying under, if you have a 40 gig card, like, while staying under 35 gig.
Okay.
So with the 3 minutes we have left, I just want to try to summarize the results of this conversation. So for the case where non-FSDB case, where people are solely relying on C2D streams, it sounds like we're just going to use the internal streams, and async collective tensor works great. So I don't know if Brian is planning to fix this specifically, but it sounds like we have a consensus here, and it just needs to be done. So that's good to me. With streams, I'm not sure. So it sounded like we had a proposal from Jansel, which is that maybe we can just ignore everything and then life is simple. Is that even that much work to ignore everything? It's just all the optimizations you have to build on top after you do that, right?
Yeah, it's all the optimizations. I think we need a little stuff to like interoperate with streams. Like, if the user has two streams, we can just say like, we're going to wait on both streams at the beginning of the graph. And then like cause the user streams to wait on our streams at the end of the graph. But that's not hard to implement.
Okay. I know you're going to be in this space, Chancellor, but I don't know specifically what you're planning to work on. Is this in the like space of things you're going to hit in the near future?
Possibly. I was hoping to look a little bit more at some of the FSDP challenges next. I was also trying to wrap up some of the FuncTools partial PRs that Vaz left. There's some correctness issues in the existing FuncTools partial stuff that I'm trying to get fixed right now.
That makes sense. How about distributed folks? Is anyone like either blocked or like working on anything adjacent to this discussion? Okay, so I'm gonna just say we're gonna let this dog lie. I'm all for doing the easy thing first. So if someone ends up needing to do this, then we should try the easy thing, I guess. And I don't know. Since no one's going to work on it, we were just manufacturing consensus. Okay, that's all the time we have for today. Any final comments? Okay, thanks everyone. See you all next week.